Sorby. I tell you, you have been straight.
All right, I believe there's a question.
Yes. So, data and results are
Okay.
for the active capacitance, we got 160 and then when we did the experimental, it was at 2.
So there was a difference between theoretical, wait, you said you got theoretical 33?
No, that's this,
Just that part?
yeah, and then
Those two you just. Wait, so what was your experimental value?
it was 116.
And your theoretical is gonna be something under 33.
It's that, and then I forgot to write this down, that's why it says 33.
Yeah, but 33 is that. So that's gonna be somewhere around 200.
Yeah, I think it was last week.
So you
It
have
started
under
at-
200.
No, but it's not due for 2 weeks. Why?
Plus
Because there's
one
no lab
over
this week and there's no lab next week.
The test is next week,
Yeah, there's no class this week.
So that's not like.
Tuesday or something.
What?
Something for the schools.
Really?
Yeah.
Nice. Why is there no one this week?
Okay, this is-
What?
Why is there no one this week?
okay, so
Because it's something
this-
for the school.
Oh, like this week,
Yeah,
this Friday we
week,
don't have.
This Friday.
Oh, okay, okay, I thought you were
Look on
next
the
week.
academic calendar, it says all campuses closed.
Nice, dude.
Yeah.
That's awesome. I didn't know that.
But
Yeah,
next
that's-
week should be.
Yeah.
What?
And then you put this.
Next week is the
you put
test.
this-
Next week's open. I'm saying this coming Friday, it's closed.
Oh,
That's awesome.
Don't we have the test? We don't have.
That, you haven't. we got
Yeah,
started
he
with
said
that.
that not, the next lab is the lab not due. You know, you understand what I'm saying? I can't speak today, you know what I'm saying?
Yeah, so.
Should probably start studying for that.
Yeah. Well, there's nothing due next week, so we just study the entire time from now until next week.
Yeah, and doing the master steps kind
Simple
of
with that,
studying.
you know, I'm gonna put it.
I'm gonna do some of the problems on the web assignment.
Yeah.
Something under 33.
Okay, so.
Ah, it's so nice, dude.
Whatever she
That
said.
just made my day.
Not have labs for 2
They're
weeks.
Oh, no, I'm not, no class on Friday.
Oh,
It's
yeah.
nice.
That, or what I have to do? Was that.
You would do.
Now you won't show up.
So if you've got-
Class.
Some flight to that. So if this is 1 farad, 1 farad, and, let's make it 10, 3 farads. Those would combine, they're parallel, so that's 20 farads. So that's the equivalent. Excuse me. 20 farad and a 3 farad in parallel.
Series.
And that would be 1/20 plus 1/3.
On the master set, number 4 and 5, the second part with the graphs. Do you have a dielectric sphere in one, and then you have a charged sphere in the other? And it's asking what the graphs look like for each from 0 to 20 centimeters. So from the very center of the sphere to like some point outside.
Okay.
So the outside of the sphere is the same in both cases, like that part of the graph?
Would be, they both have the same charge? Or they just,
Yes, they both have the same charge. One is a conductor, the other is a charged dielectric solid sphere.
I assume uniform
Yeah.
density?
Yeah.
At the outside, outside, in both cases, you treat them like point charges, and so the structures should basically look the same.
But then as far as inside,
Yeah. So as far as inside goes,
do you have to actually calculate anything for the second part of these problems, or you just want a general shape of the graph?
general shape of the graph.
To sketch the graph of the potential through the sphere from R to 0
Hey, I gave you a size and a charge. Okay, I gave you numbers.
Yeah.
So-
It's like a parabolic.
Yeah, a quick calculation.
What is a quick calculation?
Well, I know that for the conducting sphere, excess charge is hanging out on the outside.
Uh-huh.
So, in my electric field, inside is zero.
Uh-huh.
So my electric field, zero here, and then it's gonna jump up and have a 1/r² relationship. So at the surface right here, this would be, the limit as we're approaching the radius of the sphere.
Mhm.
I think I have that in here as A. This would just be KQ over R². So that's gonna be the same.
Yeah, you said the charge was, that's not the one where it's uniform throughout.
Right, this is for the conductor.
Okay, wait, that would be uniform throughout the solid sphere then, right? If it's all a conductor?
Excess charge would hang out on the outside.
No. But the dielectric is uniform throughout?
Because the charge can't be used anymore. I think that was the wording, I have to go back to the.
Uniformly charged dielectric.
The electric, yeah, so that's uniformly charged, so that's throughout. This is just conducting with,
Yeah, that says it right there,
Excess charge.
uniformly charged. Okay.
So for the conductor, the excess charges would naturally repel each other and gravitate to the outside.
Was the conductor 4 or 5?
I know that the electric field
5.
is negative del V, the gradient of the electric potential. I asked for electric field there or an electric potential?
No, you just said sketch the graph of the potential.
Potential, okay. Or, since it's a one-dimensional problem, negative dVdr. Then, if my electric field is zero, then I know the slope of my potential is zero.
Mhm.
So, if I plotted my potential versus R, outside I've got the K and Q over R relationship. Inside, well, the slope here has to be zero because the electric field is zero inside. So, flat top. For the dielectric, questions about this first.
Well, do you want us to find an exact value where it's constant though?
Yeah, yeah, and that's just K, constant, Q, I gave you the charge, and.
Oh, it's just the KQ over R for that?
Yeah.
Okay. And then it stops at the original one that we found at first, the potential of the surface, and then we can just put like a line falling away, basically?
Yeah.
Okay. all right.
Yeah. Now for the dielectric, similar to the gravitational force from math, did you do if you have a sphere of uniform mass density, what is gravitational pull inside?
I don't quite remember, but that was from physics 1.
Yeah.
Yeah.
Personally, sometimes I do it, and sometimes I don't. So,
I don't remember.
I don't know if it's possible. All right, so if I'm inside, I know that if I've got spherically symmetric charge here throughout the whole thing, but I'm interested in what is the electric field at this point right here, I know I don't have to worry about anything inside. That all I care about, reverse that. If I want to figure out the electric field here, I don't care about any of the electric field outside of that. Or any of the charges outside, I just care about what are the charges inside. Because I know that from Gauss's law, that my electric field times the electric flux is going to be equal to the enclosed charge over epsilon sub naught. Or, I'll just leave epsilon sub naught for now. It bothers me, over epsilon. It's a dielectric. So I only care about the charge that's on the inside, and so my charge on the inside, well, that's going to be the density times the volume of this piece right here, the volume of this smaller sphere.
There wouldn't be a smaller sphere, it'd be the same size of the sphere, right? Because it's like directly inside the surface, all the way to the center, because you're starting at 0.
Ask that again?
Well, it says it's going from 0 to 20 centimeters,
Right.
and the radius is 8, so wouldn't it be all the way to the center then?
It would ultimately be
To the center, all the way to the surface?
all the way to the surface.
Okay, you just have a smaller sphere.
Yeah, I was basically deriving what is the electric field inside a dielectric.
Oh, okay.
So if I look at, that's the whole sphere right there, and I wanna figure out, and there's my center, and I wanna figure out what is the electric field at this point.
Mhm.
I need to figure out how much charge is enclosed in a Gaussian surface there.
Oh, okay, which is just the charge times the volume.
The charge times the volume of this bit.
Yeah.
I know that, so this is the volume, I'm gonna make volume little r, make that little r, and make that big R. Over epsilon. The density, I gave you the charge and the outer radius, which I think I labeled as A.
Yes.
So density is going to be the total charge over the total volume. And this is going to be just the small volume. So the small. So I have whatever my total charge is over 4/3 pi r cubed. And this will be 4/3 pi little r cubed. Let me skip a step there. So those would obviously cancel out. Oh, I lost something. Just a second. A. Oh, okay. Which is equal to the electric field times the surface area. This is E times A. So 4 pi little r squared. I skipped a step there. The look on your face says I should not have skipped it.
Why are we equating it to the surface area times the electric field?
Because what I did here, from starting with Gauss's law,
Mhm.
all of this right here is working on the right-hand side.
Mhm.
The left-hand side is the electric flux, which is the integral over a surface of E dot dA.
Mhm.
So I have this Gaussian surface of radius little r.
Mhm. Which in our problem is directly under the surface.
It's, R is somewhere less than big R. Little r is less than big R.
Okay. That's where I'm kind of lost. I don't understand why we're doing it that way.
What I'm trying to derive, if I'm getting my electric potential using my electric field as a big clue.
Mhm.
If I know this, then I know what this slope looks like.
Mhm.
So that's the approach I'm taking here.
Okay.
If I am inside the dielectric, then I know that my electric field is not 0,
And it's not.
unless I'm at the very center.
Well, it's uniform though, right?
It's uniform charge density, but it's not. But because it's uniform charge density, if I'm anywhere in here, I'm ignoring the center for right now.
Mhm.
If I'm anywhere, if I'm this far away, I still have charge enclosed here. I still have charge closer to the center than the point in question.
Yeah.
So I'm deriving a formula for the electric field at that point right there.
Okay.
Just generically, some value of R that is less than big R.
And then we plug in 8 or the radius or whatever later.
Then Yeah, you'll plug that stuff in just a second. So the 4 pi, so we end up with the total charge over, say I want to solve for my electric field strength. So I have total charge, R cubed, and I have an R squared here. That's going to cancel out with 2 of those. R over 4 pi epsilon big R cubed. So that basically is a constant there. And so my electric field is directly proportional to how far I am away. So my electric field then, outside still the same as it was before. And that 1 over R squared relationship. That value right there is going to be KQ over R squared. And then it's a linear relationship there.
That's the electric field.
That's my electric field.
So it's getting stronger as it goes towards the surface.
Yes. Because when I'm at the very center, I've got electric fields, I'm surrounded by uniform electric field, they're all pointing, for any electric field here, created by a charge here, I'm gonna have one on the other side, creating an electric field in the opposite direction. So my electric field at the center is 0. So now I know what the slope is outside. I got a negative slope here. Therefore, since this was written over here, I got a negative there. Since this is negative,
Do we integrate now to find the?
yeah, you can integrate if you want to. You end up with an R squared relationship when you integrate. And so then this question, I've got something parabolic here. Which way is it actually gonna curve? And
Well, it's negative, so it'd be downwards. You can keep the negative.
and so you'd end up with something that, like that.
So that, what you just drew would be for the potential.
Yes.
So it's an upside down parabola, and then it changes at the surface area, or, yeah, the surface of the sphere, and it goes to a 1 over R relationship.
Yes.
And specifically when it comes to like the depth, I guess, of the curve for the electric field, it would be more like steep almost than the potential, because it's a 1 over R squared relationship versus.
I would assume.
Okay. So like that's something you'll be looking for, like visually.
I guess I have in the past looked for it being not quite as steep one place than another. If you have, in this particular one, if you got a couple numbers in there, I mean, that probably will speak volumes. I guess the test question I had dealt would have been on the second test, when I gave a circuit with capacitors and resistors, and you need to somehow indicate that the resistor is going to slow current with respect to time, so it won't be as steep. I think that's the time I've taken that into account. Or other questions?
I have a follow-up for the, I did it the way you told me, and I have none of
Okay.
I didn't notice.
That seems reasonable given the numbers that I saw earlier.
Okay,
I don't know if you mistyped something, but that,
that's,
it's somewhere around there.
so, it's gonna be like this, right?
It sounded like it from what you had said earlier.
Yeah. I mean, that's understandable because for one of the capacitance, we have 240.
Yeah, that, it was somehow not configured the way that you have it written out there, but I don't know. I don't suppose someone took a picture. Okay.
So, for question 1, on the Massachusetts Part B, can you explain what exactly you're looking for in terms of the electric potential at the initial location of the electron?
Alright, give me the problem.
So it says, if an electron is released from rest in a uniform external electric field,
Okay.
and assuming the electron stays in the uniform field for the duration of the problem, determine if after 1 second whether the following has increased or decreased. Explain your answer. So the first one was the electric potential energy of the system. I got that. But then the electric potential at the initial location of the electron, is that looking for like it comparatively to where it moved, or?
Yeah, so we have an electric field going, uniform electric field, you put the electron in there, I know the electron's gonna move to the right,
Yeah.
and I said, what, 1 second later?
Yes.
So 1 second later, let's say the electron is here, I'm asking about the electric potential at this point when, wait, let me see the wording.
The electric potential at the initial location of the electron. So from where it was released, what is that? But I didn't know if that was looking for something comparative.
Yeah, you are, let's see, electron was rest, uniform, as soon as electron stays in uniform, oh, that's bold-faced. Okay. So this spot right here is a certain electric potential. The electron is now here. So you're comparing that electric potential at that spot from when the electron was sitting there to when it did move. To what it is a second later.
Okay, so can we say when it's moved, the electron seeks a higher potential?
Okay.
So in my head, I would assume that the electric potential where it initially was decreased because it wants to seek a higher potential, so that the potential that I guess it was giving off.
Wait, you're comparing to speak? All right, so in the beginning of the scenario, I have an electron here at rest.
Right.
I let go. The electron is now here.